Hello everyone, my name is Enrique Saldivarcarranzae and I'm going to be talking about the effects of a probability-based green light optimized speed advisory on dilemmas on exposure. This is the agenda for today. We're going to start with motivation, then literature review, followed by objective, methodology, results, and we're going to finalize with the conclusions of the study. So let's start with motivation. Red light running is a significant cause of accidents. Just in 2017, 9% of the traffic fatalities had something to do with a signalized intersection in the United States. And this is something that we would like to minimize as much as possible. Some manufacturers, like Audi, have started to implement technologies like green light optimized speed advisory or GLOSA in their vehicles, and we were wondering what effects would these technologies have on safety. So the way Glossa usually works is that typically we will have a roadside unit or cellular device on the intersection that can interface with the controller, and we will have a vehicle that has an onboard unit or cellular device. This would allow for data transfer between the intersection and the vehicle, and information such as the intersection topology, the location, the current phase, and how long the phase is going to last can be transmitted from one side to the other. After this is done, the vehicle can then process the data and calculate an optimal approaching speed so the vehicle can get to the traffic signal during the green phase of the cycle. There is room for improvement in the sense that few glossy studies have taken into consideration actuated traffic signals. Added to this, the negative effects of latencies can also be reduced. Now let's look at the literature review. Parsonson and Seeger were able to identify that rear-end collisions and right-angle crashes are a result of dilemma zone exposure. The dilemma zone is an area in which after an onset of yellow, motorists are not sure if they should continue or stop. This uncertainty increases the risk of an accident. We will look with more detail into this topic later on. Zimmerman was able to mitigate the incursion of vehicles in this zone by controlling signal phases and warning drivers of a possible risk. Stallman found out that glossy simulation studies tend to overestimate transmission ranges and message delivery ratios, and it is also important to note that there are glossy systems that aim to improve specific aspects, like travel time or fuel consumption. The objectives of the study were to develop a glossy system that is resilient to high latency environments and that accommodates the stochasticity of actuated traffic signals, to develop 4 different glossy estimation strategies for evaluation, and to virtually drive a corridor using each strategy over a few 100,000 trips to estimate the number of heartbreaking events and the number of red light crossings. The novelty of the study is that only a one-time download of historic data is required to provide advisory for the complete route, that the system presents capabilities for actuated traffic signals, and that we're focusing on the effects that the probability-based glossa has on safety. Now we can move on to the methodology. The testing route in which the virtual drives were carried out is a segment of US 231 located in West Lafayette, Indiana, that goes from US 52 to South River Road. You can see in the map all the intersections that are in this segment of the road. And if we had 2 timing plans, one that goes from 8:15 a.m. to 9 a.m. and another one that goes from 9:15 a.m. to 2:45 p.m. To develop the probability-based glossa, we needed to access the historic intersections phase events data. So we utilized high-resolution traffic signal controller data, which saves events in log files with a tenth of a second resolution. This way we could know what phases were on at a specific traffic signal at a specific time of day, and we could then calculate probabilities. For example, if we wanted to travel on Tuesday 19th of March 2019 between 8:15 a.m. and 9 a.m., then we will be looking at a previous week's information with the same time of day, so between 8:15 a.m. and 9 a.m., and the same day of week timing plan. So if we were traveling on a Tuesday, that means we will be looking at events that occurred between Monday and Thursday. This is because the traffic signals have similar timing plans for these days. Now we're looking at one of the first traffic signal cycles in the current time of day plan when going northbound on Martin Gisca Drive on the Monday before our intended trip. If we focus on a specific time inside the cycle, we can see how different events occur throughout the time of day period. We can see how for the time in cycle 70, one of the first events is a red light. But as we move forward, we start to see different events. At the end, to calculate the probability of the traffic signal to be green at a specific timing cycle, we count how many green events occurred for the entire day-of-week plan for the same time of day period and divide this number by the total number of cycles that were analyzed. By just looking at a few cycles on Monday 11th, we could predict that the probability of the traffic signal to be green at a time in cycle 70 will be close to 50%. Now we can see the probability of the traffic signal of Martijiska Drive to be green at different timing cycles. We can see how there is a range of time roughly between the timing cycle 30 and 50 in which we have a 100% probability of a green phase. If we take a closer look at the probability of green at the timing cycle 70, we can see that it is close to 50%, as we had predicted. Nevertheless, we have to translate the obtained probability profile to a binary advisory. To do so, we make use of thresholds that will make our probability either a green or no green prediction. With a 75th percentile threshold, the predicted green time will look like this. Whereas, with a 25th percentile threshold, the predicted green time would look like this. The different lengths of the expected green time will have different consequences on the advisory outcome. For example, let's suppose that we have to provide a speed advisory based on the previously proposed thresholds. The traffic signal cycle at the top is the real event that occurs at the traffic signal. Because of our starting point, the shaded area are not reachable, so anything outside of it is a possible outcome. So, based on the 75th percentile threshold, the green phase is not reachable, so the driver would be advised to stop. Nevertheless, in reality, the vehicle could have made it through green. This makes advisories based on high thresholds to be conservative advisories. On the other hand, an advisory based on the 25th percentile threshold would provide the correct advisory of going through green. Now, let's analyze a different scenario in which the green of the traffic signal appears sooner. Using the same conservative threshold at the 75th percentile, this time the advisory will have a correct prediction and would advise the driver to stop. Nevertheless, the prediction based on the 25th percentile threshold sees arrival on green as a feasible outcome, which, in this case, would result on a red light running event. This makes advisories based on low thresholds to be aggressive advisories. This is a video that shows how the traffic signal phase prediction works. In this case, we're utilizing a 70th percentile threshold. We can see the vehicle's current speed and the current probability of arrival on green. I'm going to let it run again so you can appreciate with more time what's going on. To better understand the effects that different thresholds have on GLOSA, we calculated the prediction outcome of an advisory given to a vehicle located 200 feet behind the stop bar when approaching Martin Gisca Drive on March 18th at different starting times. On the y-axis, we have the different thresholds in which the advisory is based, and on the x-axis, we have the different starting times. On the top, we display the actual events at arrival. On blue, the successful green predictions are represented. On gray, the unsuccessful green predictions are shown. And on white, We have the events in which green was not predicted. We can see how a conservative advisory stopped predicting green before the onset of yellow occurred. We can see that the correct end of green prediction occurs when we base our advisory on a threshold roughly located at the 70th percentile. An advisory based on a 50th percentile threshold would keep predicting arrival on green as a possible outcome even shortly after the onset of yellow has occurred. Lastly, similar to the advisory based on the 50th percentile, an aggressive advisory based on a 25th percentile threshold will keep predicting arrival on green as a possible outcome even almost at the end of yellow. There are 4 possible events after an onset of yellow occurs. We can have non-heartbreaking events, heartbreakings, yellow light crossings, and red light crossings. To understand the effects that glossa has on safety during the end of green, it is necessary to understand the concept of dilemma zone. As shown in the figure, dilemma zone has been defined as the area in which more than 10% of drivers, when less than 90, would decide to stop. The most critical point of the dilemma zone is when half of the drivers would decide to stop and the other half would decide to keep going. At this point, rear-end crashes are more likely. We can calculate a vehicle's probability of stopping based on its speed and distance to the stop bar by utilizing a binary regression function that has been designed for light vehicles. If we focus at the most critical point, when 50% of the vehicles would stop, we can obtain a function that provides information on what speed a vehicle needs to be traveling at a certain distance from the stop bar to be located at this critical point. Here, we can see the probability of a vehicle to stop depending on their speed and how far away they are from the stop bar. The graph at the bottom shows at what speed a vehicle at a given distance will have a 50% probability of stopping. Vehicles going faster than its speed will be more likely to decide to cross the intersection, whereas vehicles going slower will be more likely to decide to stop. Regarding the virtual drives, 486,000 trips were driven, phase events were taken from each signal controller's historic data, different glossa strategies were tested for each drive, including unadvised, aggressive advisory, balanced advisory, and conservative advisory, and the simulation period was from March 18th to March 21st, 2019. This means that the probabilities were calculated from March 11th to March 14th, 2019. The way unadvised trajectories were carried out was with the vehicle starting at a stop condition at the beginning of the route. Then, the vehicle started accelerating at a 3 miles per hour per second rate until reaching the speed limit. At this point, the vehicle simply maintains this speed until a yellow light or a red light are seen. If, for example, the vehicle saw an unexpected onset of yellow 300 feet away from the stop bar while traveling at 50 miles per hour, the speed and distance would then be compared to the critical speed function. If the speed at the specified distance is lower than the critical speed, then the vehicle stops in the virtual drive. Nevertheless, if we plotted this point in the binary regression function, we would obtain the real probability of this vehicle to stop. For this reason, the vehicle's speed and distance to the stop bar when the onset of yellow occurred are saved. At the end, post-processing calculations were done with the entire analysis data to obtain how many vehicles decided to stop and under which circumstances. The way advised trajectories were carried out is similar to the unadvised trajectories. First, the vehicle starts at a stop condition at the beginning of the route. Then, the vehicle starts accelerating at a 3 miles per hour per second rate until reaching the speed limit. At this point, we start using glossa. If green is not predicted to be possibly reached, then the driver is advised to prepare to stop. If green is predicted to be possibly reached, then the vehicle modifies its speed at a 1 mile per hour per second rate within a permitted speed range that goes from the speed limit to an specified minimum speed. If, while predicting an arrival on green, the vehicle saw an unexpected onset of yellow 240 feet away from the stop bar while traveling at 45 miles per hour, The speed and distance would then be compared to the critical speed function. If the speed at the specified distance is faster than the critical speed, then the vehicle keeps going in the virtual drive. Nevertheless, if we plotted this point in the binary regression function, we would obtain the real probability of this vehicle to stop, or in this case, to keep going. Finally, we save the vehicle's speed and distance to the stop bar when the unexpected onset of yellow occurred with post-processing purposes. Now let's look at the results. Here we can see the total number of unexpected onsets of yellow at different distances from the stop bar for unadvised and advised approaches with an aggressive probability threshold. The probability of stopping of a vehicle traveling at 55 miles per hour is overlaid on the bar graphs to help visualize what was the behavior of the drivers for the different scenarios. We can easily notice the significant reduction of unexpected onsets of yellow by utilizing an aggressive advisory. This translates into less heartbreaking events and red light crossings since the drivers have more information on the future state of the traffic signal. As the advisory goes from aggressive to balanced and then conservative, we keep seeing a reduction in the total number of unexpected onsets of yellow, further decreasing red light crossings and heartbreaking events. Here we see a summary of the results when the minimum allowed speed was 50 miles per hour. We can see a reduction in heartbreaking events from 1,699 when traveling unadvised to only 112 when having a conservative advisory. There is also a reduction from 708 red light crossing events to only 30. The downside of the advisory is that it increases the travel time since it sometimes makes drivers slow down unnecessarily. The average travel time went from 385 seconds when traveling unadvised to 394 seconds when using a conservative advisory. So there was only a 9-second increase. In conclusion, the proposed probability-based GLOSA system showed that it would improve safety during the end of green, since reductions of 96% of red light crossings and 93% of heartbreaking events were accomplished. Travel time only increased by 24 seconds in the worst case. The future work consists of incorporating fuel consumption models and performing field tests. Thank you for your attention. If you have any questions, feel free to reach out.